In this video, I am going to explain the tautology laws. These are very important laws because they are used to eliminate any unused logic gates. Let's start with the first set of tautology laws. And the first set is this. If we have A and A, that is equivalent to A. And if we have A or A, that is equivalent to A. Now, what is the meaning of these two laws? In order to explain them better, I am going to sketch here the truth tables of both the AND gate and the OR gate. So if we have the AND gate and we have 0, 0, 0, 1, 1, 0, 1, 1, the output is 0, 0, 0, 1. And if I draw the OR gate here, actually not the OR gate, but the truth table for the OR gate, the OR gate will give this output. Now what we are saying here is that if we have A and A, so both inputs are the same, as you can see here and here, then might as well just remove the AND gate and just write A, because as you can see here, when both inputs are the same, the output is the same as the inputs. The same applies for the OR version of the same tautology law. A or A gives us an A. In fact, if we have a look at the OR gate here, when we have 0 or 0, so both inputs are the same, it will give us the same output, 0. And when we have 1 or 1, so both inputs are the same as well, we will have the same output as well. Therefore, when we have A and A or A, we can eliminate the logic gate and just use one input. The second set of tautology laws is this one. A or A naught gives us always a 1. A and A naught gives us always a 0. And to explain these, it's best if we do some sketches. So let's start with a sketch for the A or A naught. So if we have A going through an OR gate, we are saying that if we input to it, it's not equivalent of the A, this will always give us a 1. And I think it's quite obvious why this happens. Let's say that A is 0. If A is 0, then here a 0 is being inputted in this OR gate. Since we have a NOT gate here, this 0 is being inverted to 1. Therefore, we always have a 1 being inputted in this OR gate. We know that whenever we have a 1 being inputted in an OR gate, the output of the OR is always a 1. Therefore, this law holds. We can use the same reasoning for the other tautology law. This time we have the AND gate. So we have an AND gate. We have A being inputted in the AND gate, and we have its not equivalent being inputted as well. And in this scenario, let's say A is 0. If A is 0, then we know that since there's a 0 being inputted in an AND gate, the AND will always give us a 0. As you can see here, when there is a 0, the output is always a 0. On the other hand, if we input a 1, so let's say A is giving a 1. Even though here we have 1 being inputted, since there is a NOT gate, if there is a 1 here, since there is a NOT gate, this 1 will be inverted to 0, and therefore here in this AND gate we are getting a 0 input, which means that there is a 0, therefore the AND gate will give us a 0. Therefore this Boolean expression holds as well. The other two tautology laws, or two sets of tautology laws, are very similar to the ones that I have already explained. But this time, instead of getting inputs from the same wire, from the same input, we are going to give them directly zeros and ones. So if we have a 0 and an A, that is always going to give us a 0. And when we have 1 and an A, this is always going to give us an A. Why? The same reasoning applies. So if we have, for example, an AND gate, and we are inputting a 0 there and A there, A can be 0 or 1, but we know that if there's a 0 going through an AND gate, the result is always going to be a 0. Now if we focus on this one, if we have another AND gate and we have a 1 going through the AND gate, and then we have A, where A can be either 0 or 1. If A happens to be a 0, then 1 and 0 will give us a 0, which is equivalent to A. And if A happens to be a 1, 1 and 1 will give us a 1, which happens to be the same as A. Therefore, in that case, the output is always equivalent to A. The last set of tautology laws are the ones used for the OR gate. So 1 or A, they will always give us a 1, and 0 or A, they will always give us an A. And if we sketch these gates, so if we do an OR gate, and I am referring to the first one, if we have a 1 going through the OR gate, irrelevant what is the other output, since there is a 1, the OR gate will always give us a 1. On the other hand, if we have an OR gate and there's a 0 going through that OR gate, then the output depends on the other input. If the other input happens to be a 0 as well, we know that 0 or 0 gives us a 0. But if A happens to be a 1, we know that 0 or 1 gives us a 1. Therefore, the output is equivalent to A.